everyone, welcome back to the channel. Today, in the final part of Windows System Monitoring Practical Series, we will perform advanced monitoring using Resource Monitor. We will analyze process activity, services, handles, memory pressure, hard faults, disk activity, and file level operations. This is one of the most important tools used during advanced troubleshooting and performance investigations. So let's start right now. Resource Monitor provides more granular visibility compared to Task Manager. This is extremely useful for advanced troubleshooting and performance analysis. Now we are inside the CPU tab of Resource Monitor. Compared to Task Manager, Resource Monitor provides much deeper visibility into process activity, services, handles, and system resource usage. This tool is extremely useful during advanced troubleshooting and performance investigation. In the process section, we can observe all active processes currently utilizing CPU resources. Each process is assigned with a process ID, also known as PID, which uniquely identifies that running process inside Windows. The CPU column shows current processor consumption, while average CPU displays long-term utilization trends. Thread represent execution units running inside the process. For example, here we can see the Splunk service running with a process called splunk.exe. Splunk uses this process for indexing, searching, and managing log data. This demonstrates how monitoring tools themselves also consume system resources. In enterprise environments, administrators often analyze high CPU processes to identify bottlenecks, unstable applications, or suspicious activity. Services. Below the processes section, we can see related Windows services. Services are background components that continue running even when no user is actively interacting with the system. In this case, the Splunk service is associated with the Splunk kd.exe process. This relationship helps administrators identify which service belongs to which running process. During incident response, analysts often trace suspicious services back to their parent process to understand system behavior. Associate handles. Now we are viewing associated handles. A handle is essentially a reference that a process used to interact with system resources such as files, directories, registry objects, or devices. In simple terms, handles show what resources a process currently has access to. Here we can observe that Splunk process currently have active access to multiple log files, database files, and directories. This helps administrators understand what the process is actively reading or writing. For example, if a process logs a file, consumes excessive resources, or behaves suspiciously, associated handles help investigators identify exact which resources are being accessed. In cybersecurity investigations, analysts sometimes inspect handles to detect malicious file access, persistent mechanism, or unauthorized resource usage. On the right side, we can observe real-time CPU utilization graph for individual processor cores. These graphs help you identify workload distribution across the CPU. If one core remains consistently overloaded while other remain idle, it may indicate inefficient workload balancing. In enterprise troubleshooting. These metrics help diagnose performance bottlenecks, software inefficiencies, and resource contention issues. Now we are inside the memory tab of Resource Monitor. This section provides detailed visibility into how processes are consuming physical memory and virtual memory resources. Compared to Task Manager, this view provides deeper memory analysis useful for troubleshooting system slowdowns and memory bottlenecks. In the processes section, we can observe applications currently consuming memory resources. The working set column represents the amount of physical RAM currently allocated to the process. The commit column represents total committed virtual memory allocated to the process. Application with excessively high memory consumption may reduce overall system responsiveness. Hard faults are one of the most important metrics here. A hard fault occurs when Windows cannot find required data in physical memory and must retrieve it from disk storage or the paging file. Since disk access is significantly slower than RAM access, excessive hard faults can reduce system performance. A small number of hard faults is completely normal. However, consistently high hard fault activity may indicate insufficient RAM or excessive memory usage. For example, if multiple heavy applications are running simultaneously, Windows may start relying more heavily on virtual memory, increasing hard faults. Security monitoring tools, browsers, virtual machines, and SIM platforms often consume significant memory resources in enterprise environments. Physical memory bar provides a virtual representation of how system memory is being utilized. Hardware reserved memory is allocated for hardware level operations and is unavailable for normal applications. The in use represents memory actively consumed by running processes and the operating system. Modified memory contains data that must be written to disk before it can be reused. Standby memory contains cached data that Windows may quickly reuse if required. Free memory is currently unused physical RAM available for immediate allocation. Windows Memory Management dynamically reallocates memory depending on workload requirements. On the right side, we can see real-time memory utilization graph. These graphs help administrators identify memory pressure, paging activity, and resource consumption trend over time. Overall, the helps administrators diagnose RAM bottleneck, excessive paging activity, and memory intensive applications. Now comes the disk tab of Resource Monitor. This section provides detailed visibility into disk inputs and output operations occurring across the system. Disk monitoring is extremely important for identifying storage bottlenecks, slow applications, and heavy file activity. In the upper section, we can observe processes currently performing disk operations. The read and write columns display how much data each process is reading from or writing to storage. The disk activity section displays individual file currently being accessed by processes. This provides extremely granular visibility into file level read and write operations. The read column represents data being retrieved from storage, while the write column represents data being written to disk. In cybersecurity investigations, file activity analysis helps identify suspicious file access patterns, ransomware activity, unauthorized writes, or abnormal storage behavior. One of the most important storage metrics is disk queue length. This represents the number of disk operations waiting to be processed by the storage device. If queue length remains consistently high, it may indicate storage condensation or disk bottleneck. Short spikes are normal during heavy file activity. However, continuously high queue length may impact overall system responsiveness. The storage section provides overall disk utilization metrics including active time, available storage capacity, and queue length. The real-time graph on the right side helps administrators visualize disk activity patterns and identify sudden spikes in storage usage. Overall, the disk tab provides deep visibility into file operations, storage utilization, and disk performance troubleshooting. In this practical series, we monitored CPU, memory, and disk utilization using Task Manager and Resource Monitor. These monitoring fundamentals are extremely important for IT support, system administration, SOC operations, and cybersecurity workflows. If you found this practical useful, stay connected for upcoming labs on Event Viewer, Sysmon, Performance Monitor, SimTools, and Windows internals. Thank you.